All right, let's do a few more. We'll hit a couple of these in A. You've got a 6 ohm lamp. It needs 25 amps of current to operate. In which circuit would the lamp operate when the switch is closed, right? So if we look at this one right here, if we close this switch and I'm an electron here, when I get to my Y intersection, right, I can either go this way and have a 6 ohm wall to climb over and come around, or I can go this way and have nothing to go over, right? So electrons will take the path of least resistance. Now, that we can take that a couple of ways. More electrons will go on a slightly easier path. If you've got two pathways, like maybe there's a 3 ohm resistor here, right, then more of the electrons are going to go the 3 ohm side and less electrons are going to go the 6 ohm side, but some would go both. But if there's no resistance over here, pretty much none of the electrons are going to go this way, right? Now, technically, there's some resistance in the wire, so you'd get a very small amount, but you've just made a short here, right? So this is a short. When you short something out, you bypass the load, and the electrons are going to go through the short. All right, so I look at this one. If I close this circuit, right, if I close this one, I have a short right here, so that would not work. When the switch is open, right, you could have electrons go this route, right? So before I closed the switch, again, you made a short. Same thing with this one. Electrons could go here first. When we do this one, when we close this one, hey, now it's got one loop, right? So the C looks good. When I do this one, again, I've made a short in parallel, so that one's no good. So C is the one that makes sense. Questions 9 and 10, refer to the following unknown resistor, a 120 volt source, ammeter is connected to this, 0.5 amps. Well, I know V equals IR, right? So I know V over I equals R. So since my total resistance then must be 120 divided by 0.5, so my total resistance is 240. You've got 50 right here. This is in series, so we add them together. So 50 plus X is 240, so X must be 190 ohms, right? 9, calculate the resistance of the circuit shown. I just did that. 240 is the total. Determine the resistance here. I'm not reading my own worksheet, right? Anyway, there's that, right? 11 and 13 refer to the following ones here. You've got a 3 ohm resistor. Where's my 3 ohm resistor? So this was, okay, so this must be 3 ohm resistor. Oh, no, that's the unknown resistor. You have a 3 ohm resistor, an unknown resistor, and 2 ammeters that are connected and shown. Determine the equivalent resistance. So here, I need to figure out what all is going on here. So my total current, this one's definitely a little bit more challenging. I've got my total current here. My current is going to split, and some of it's going to go here, and some of it's going to go here. And we've got a 12 volt source. Both of these will get 12 volts, right? So that's the key there, is since my electrons split, we have to come back here with 12 volts. So that means for my V equals IR, 12 volts over 3 ohms is going to give me 4 amps for this one. If 4 of my amps went this way, then my other 1 amp goes this way. Amps are flow. So if my current in these two needs to add up to this one. So I have 1 amp going here, which means if I have 12 volts divided by 1 amp, my resistance must be 12 ohms. So this must be a 12 ohm resistor here. So the current in this one is 4 amps, and my unknown resistor is 12 ohms, right? So there's that one. As they start to get a little bit more complicated, that's the ones we've already done. We'll do a couple of these. You've got all the answers here, right? So it's not like I'm helping you cheat and stuff. But some of these are a little more challenging. If I don't go through one that you want answers to, just jump on a Google Meet and we'll do that, because I'm not going to go through all these because it takes some time. A load across a 50 volt battery consists of a series combination of 2 lamps with these 2 resistances. Find the total resistance. So since they're in series, I'm just going to add those together. So 125 plus 225 gives us 350. Find the current. So it's 50 divided by 350. So that is 0.14. Find the potential difference across the 125 lamp. So then remember, we have to spin this 50 volts across these 2. So I'm going to do 0.14 times V equals IR. So 0.14 times 125 times 125. So of my volts, 17 of them, 17.8 go across the first one. It should make sense that it's less than half because that's a smaller one. If I did my other one, 50 volts times 225, That gives, nope, that's not 50 volts times 225, sorry, 0.14 times 225. That gives us the rest of our 50, the 31.5, right? Okay, so then we go, let's see. We'll jump down here to 17. Load across a 12-volt battery consists of a series combination of 3 resistors. That's very similar to what we just did. 2 resistors, here we go. 2 resistors, one is 12 and the other is 18, is in parallel, right? So we've got parallel here, so it's one like that. Not that you can tell what's going on in my drawing. 12 at 18 ohms, right? Let's see, what is the equivalent resistance? So I add up 1 divided by 12 plus 1 divided by 18, right? And then I take the inverse of that, and that's going to be 7.2. Whoops, I'm on this one, 7.2. Right? 3 resistors of 12, 1 divided by 12, plus 1 divided by 12, plus 1 divided by 12, or I could have just times it by 3, right? Take the inverse of that, and we get 4. Right? Okay, 21, household stuff is more interesting. Right, 110 volt household current. You will sometimes see 110 volts listed for household stuff. You will sometimes see 120 volt listed for household stuff. That is because it varies from 110 to 120. It fluctuates a little bit, right? It fluctuates like that. And like the max, I believe, is 120, but the average is 110. Right, so it does fluctuate a little bit as it's going through there. Right, 110 volt household circuit contains a 1200 watt. Oh, we haven't done power yet. Don't worry about the power ones this week. We will jump in and do power next week. Right, are all of these power stuffs? Let's see. Let's go ahead and do one more. Like 23. 3 resistors, 15, 9, and 8 are connected in series. Their combination is in parallel with R3. What is the load across the 6 volt thing? So if we draw this guy, we've got parallel. I've got resistor 1, resistor 2. Oh, whoops. Resistor 1 and 2. So this guy is 15. This one's 9. This one's 8. So I do 1 divided by 15 plus 1 divided by 9. Inverse that. So my equivalent resistor, oh, I can't draw straight lines today, is 5.6, and this one is 8. This is a 6-volt battery, so we draw the circuit. The total resistance of the load, so now since those guys, oh, whoops, I did those two like they were in parallel. That was dumb. 15 plus 9 for those two. I apologize. I get going quick on these guys. So the equivalent to this one is 24. The equivalent to this one is where I do the 1 divided by 24 plus 1 divided by 8, inverse that. So the equivalent is 6 volts. Hey, look at that. Isn't that cute? We have I cannot draw this thing at all with a 6 ohm resistor, right? So that's the equivalent. The total resistance of the load is just 6 ohms. What is the current in R3? So if we know this, I'm going to go to this drawing for this one because this is my R3. I know it's going to get 6 volts. So we're going to do 6 volts divided by 8 ohms, and the current there is going to be 0.75. What is the potential difference across R2? Well, this one we're going to have to work a little harder at getting because here I'm going to need to know because the whole voltage will get spent here, but some of it here and some of it here kind of thing. So it'd be helpful to know what the current is there. So the total current is 1 amp. So that means that across this one, we get 0.25 amps because this one got 0.75 amps, right? So we've got our 2 amperages there. So then we go 0.25 times that second resistor, which was the 9. And so it's 2.25. If we did 0.25 times 15, we'll get the rest of the 6 volts, 3.75, right? Because plus 2.25, that gets us our full 6 volts. Oh, whoops, I had 2.25 instead of 2.25. Plus 3.75, right? That's 6. So 2.25 volts for this one right here. right? I don't know if I'm going way too slow through these or way too fast. Normally kids pick up on these pretty well, but normally you're able to talk to each other as you're doing these. So it might not be a bad idea to, like, I don't know, do the house party thing or whatever you're doing as you're going through these and work with a buddy on these. You just kind of got to work through a few of them to keep track of, am I adding these or adding the inverse of these or whatever. Like I said, normally kids catch on to these pretty quick. I feel like we're going through them kind of slow and you might be bored with them, but this definitely might be a more challenging thing to be doing on your own. So, come and see me virtually, right? If you're having some trouble, and hopefully things are going well for you.